So, ladies and gentlemen, you are welcome. So today we are going to continue from where we stopped from electrochemistry. So in today's video, we are going to look at the concept of galvanic cell. So what is a galvanic cell? It's a device in which chemical energy is converted into electrical energy. And it is used as a spontaneous redox reaction to produce an electrical current that can be used to generate an energy or to do a work. So generally in a galvanic cell, we have a chemical energy, and this chemical energy is nothing but a redox reaction. A redox reaction. So a redox reaction in galvanic cell is used to convert or is converted into electrical energy. Is converted into electrical energy using a galvanic cell. So a device that converts chemical energy into electrical energy is what you call a galvanic cell. And of course, it uses the spontaneous redox reaction that generates an electrical current, which is used to do work. So that is a galvanic cell. So, and then the next thing that we are going to look at after the galvanic cell is the nature of the galvanic cell. So galvanic cell is made of an anode. It's made of anodes and cathodes. And in the anode, there is an reducing agent, and in the cathode, there is oxidizing agent. So what is reducing agent? From our previous class, we discussed about that reducing agent is an electron donor, while reducing agent is an electron acceptor. So therefore, any species that donate electrons is called a reducing agent, and the process is called oxidation. So oxidation is a process whereby a species loses an electron. So a reducing agent, it means that a species that undergo what you call oxidation. And then an oxidizing agent is a species that undergo reduction because it is electron acceptor that it is gain electrons. So in galvanic cell, we have anode and we have cathode. And of course, oxidation takes place at the anode, while at the cathode, reduction takes place. So this is just a brief description of a galvanic cell, and there is a porous disc. Another way we call it salt bridge. What is the importance of the cell bridge? It helps to connect the two half cell, that is the cathode half cell and then another half cell. So it helps to connect them, as we can see from here. So this is a galvanic cell. This is how it looks like, and it converts chemical energy into electrical energy. So then the next thing is, of course, a brief description of the galvanic cell as I started. So oxidation takes place at the anode, and then reduction takes place at the cathode. And then there is a cell bridge which actually linked the two half cell, that is cathode and the anode, at the same time. So this cell bridge it is one application. It has so many applications in galvanic cell, and let's look at the applications of this cell bridge in a galvanic cell. Okay, and in addition, of course, let's look at it clearly and how it happens. So you see, this is a galvanic cell, and this is a voltmeter, and there is a cell bridge. An example of the cell bridge that is used in this galvanic cell is potassium chloride, and then we have our electrolyte. At the anode, we have zinc sulfate, and of course this zinc sulfate always dissociates or ionize to produce zinc 2+ and the sulfate ion. And then we have copper 2+, which also which actually produce as a result of ionization of copper sulfate to copper ion and also sulfate ion. And of course, this is where you have your reduction. Look at it. If you can see clearly here, copper gained 2 electrons at the cathode. So it means that it undergo reduction. It undergoes reduction. And then of course here you can see that it is a zinc, so it loses 2 electrons. It means that it undergoes oxidation. It undergoes oxidation. So then the next thing after this is of course the salt bridge. So a salt bridge is a laboratory device that used to connect, two half cell, that is cathode and anode. And if you can look at it clearly from the previous slide, you can see that it linked the two electrodes together, that is cathode and anode. And then it should be inert. That means that it shouldn't be participating in either oxidation or reduction reaction. So it is inert. It doesn't undergo any reaction, and it should not react with the anode, cathode, or the solution. So it shouldn't react with that. And then the salt bridge should not be precipitated. So it should not be precipitated. And what is the main functions of this salt bridge is actually complete the circuits of a cell, is to complete the circuit of a cell, and then to also maintain the neutrality. And examples of the salt bridge, we have sodium chloride, potassium chloride, and then potassium nitrate. So these are the examples of the salt bridge that are usually used in galvanic cell. So and then the next thing is a cell potential. So a cell potential is actually a driving force, or is an energy that they use in transferring, or that used in the transfer of electrons from anode to the cathode. So that is what you call a cell potential. It's a driving force, or is an energy that used to transfer electrons from anode to the cathode, and that is what you call cell potential. Cell potential is an energy that transfer electrons. It transfer electrons from anodes to cathodes. And of course, so that is a galvanic. So in a galvanic cell, it consists of an oxidizing agent, that is a cathode half cell, and then a reducing agent, which is the anode half cell. And of course, there is an electron flow from anodes to the cathodes. So the driving force that allow electrons to flow from the anode to the cathode is called electromotive force, or a cell potential, and it has a unit. So the unit for a cell potential is volt, which is exactly the same as joule per coulomb. So 1 voltage is the same thing as 1 joule per coulomb. So that is what you call a cell potential. And then in addition to this, we have what you call a standard reduction potential. So a standard reduction potential is represented with epsilon naught. Is represented with an epsilon naught. And of course, when we set the values of the standard electrode potential are usually given in a table of the half cell potential for the reduction half cell. And of course, whenever we set a standard electrode potential, it means that it's a cell potential that occur under standard condition. And the standard condition of the of a cell potential is one. It occurs under standard condition, that is 1 molar concentration, 1 atm pressure, and then room temperature, which is 25 degrees centigrade. So these are the standard condition that we consider cell potential as the standard reduction potential. So then when a half cell is reversed, so generally, okay, before then, let me just show us the table for the standard electrode potential. Let me show the table for the standard electrode potential, and of course that will really help. So this is actually the table for the standard electrode potential, where we have a positive value and we have negative value, and we also have a reference value. The reference value is hydrogen standard electrode potential. Hydrogen standard electrode potential. This is the reference value, and of course you can see clearly this is an increasing from here to here, is an increasing of an oxidizing agent. So it means that the higher the value, or the more, or the higher the value of the standard electrode potential, it means that the higher the oxidizing agent property of a species. And of course, we said that when we have actually when you have an oxidizing agent, it means that that species is set to undergo what we call reduction. What we call reduction. So, but now the issue is when we have a cell potential. So, cell potential always will give us an idea whether, because sometimes you can have maybe two reactions, three reactions, or three species, and each of them have their own cell potential. So you can use the cell potential to know whether the species will undergo reduction, oxidation. So like for example, we know that oxidizing agent undergo reduction. So the higher the value of a cell potential, it means that the higher the oxidizing ability of that particular species. So therefore, if you have two reactions, the one with higher cell potential, it means that it will undergo reduction. And the one with a lower electrode potential will undergo oxidation, because the lower the standard potential, it means also in that case, the more the reducing ability of that particular species. So maybe you can have so many cases, like for example, let's say you now have this species, you have iron 3 plus, and then you have copper 2 plus. So if you ask between these two, which one undergo oxidation and which one undergo reduction? So first, look at it between this and this, which one have a lower value. So copper have a lower value. So since it has a lower value, so it will undergo oxidation. And the one with higher value will undergo reduction. So this is very, very important. And we have standard hydrogen electron potential. So now, what happened in the case where we have like for example, so when you have a half cell and the half cell is reversed, then the algebraic sign of the standard electrode potential will change. So assuming now, what this means is that, let's say you have zinc 2 plus 2 electrons, and then you now have zinc. So if the value for this, let's say if the value of this is plus 1.1 volts. So, but now maybe at the end, you now decide, okay, maybe you'll reverse it. So after reversing it, it means that you are changing the product to the reactant and then the reactant to the product, meaning that it will become zinc. Then we have zinc 2 plus, then plus 2 electrons. So you see it, you reverse it. So when you reverse it, the sign of the standard electrode potential will change. So here is positive. So since you reverse it, it is now going to change to negative. That is minus 1.1 volt. That is what happened in this case. And of course, you can have a situation, especially when trying to cancel the electrons that are fair, or the number of electrons that are either as gained or lost in the redox reaction. So in some cases, you may need to do some kind of multiplication for you to neutralize them. So in that case, when a half cell is multiplied by an integer, then the value of the standard electrode potential will remain the same. You are not multiplying, it will remain the same. And then of course, the galvanic cell runs spontaneously. It runs spontaneously in the direction that gives a positive value for the standard electrode potential. So what does that mean? It means that if you have standard electrode potential that is positive, that tells you that the reaction will take place spontaneously. It will take place. It gives you an idea of the feasibility of the reaction. Okay, and then the next thing now that we are going to look at after this is, of course, we have actually looked at this. So now this is an example. So this is an example where we have iron 3 plus copper to give us copper 2 plus iron 2 plus. So these are the half reactions. So in this half reaction, of course, this is what we have. So we have iron 3 plus iron 2 plus, and then we have copper. We have copper. This is copper 2 plus, and then plus 2 electrons. So now, so you have copper 2 plus, then of course plus 2 electrons, then it will give us the neutral copper. So now the first thing that we need to ask ourselves in this situation is that, okay, in this case, we have the values. We have 0.77 and 0.33. So now the question is which one will undergo oxidation and which one undergo reduction. So the higher the value, then the higher the oxidizing property. So it means that this one will undergo reduction. So the higher the value, because it has higher value, so it will undergo reduction. And the one with lower value, it's going to undergo oxidation. So this is what we have. This is what we have. So now, this is the half cell, this one is the half cell, and this one is half cell on its own. But now, if you look at this thing from here, we just only here indicate that, okay, it will undergo oxidation because of this value. But if you look at from here to here, it's not oxidation because there is an increase, there is a decrease in oxidation number, or there is a gain of electrons. So it means that it's a reduction. So therefore, as a result of this, we have to reverse this. So here we have copper 2, and sorry, we have copper, then we will now change to copper 2 plus. So here is having positive value. So because we interchange it, then it is now going to be negative. It is now going to be negative. So here we have 2 electrons, but here is 1 electron. So, but we want to neutralize the number of electrons. So what we are going to do is to take this coefficient of electrons here and multiply it through by this equation 1. And then the coefficient of the equation 1, that is the electrons in equation 1, which is 1, you also multiply it with this. So you multiply it. So the first equation is multiplied by 2. So of course, and at the end, this is what we are going to have. This is what we are going to have. So after we have this, then what next? You have to add this. You have to add the overall of this reaction. You have to add this plus this, and you cancel the number of electrons. And of course, even from here, you can clearly see that these are the reactant and these are the reactant. And these electrons, of course, will cancel these 2 electrons automatically. So here we have copper plus 2 molecules of iron 2 plus. Then it will now give us, then we'll now take this, which is iron 2 plus, and then plus copper 2 plus. So this one will be the overall reaction. So then this is what happens. So let's look at the next slides. So you see here we have 2 molecules of iron 3 plus. So we have them here like this. Then we now add them. So we know that this is our cathode, that is reduction, and this is our anode oxidation. So the balance cell. So this is the balance cell. So you add this together. We have to add them. So after we add them, that is what I did in the previous slide. We add this. So we add this and this. So then the next thing is actually to calculate the cell potential, So how are we going to calculate the cell potential? So because this one changed to negative, this one is for the cathode and this one is for the anode. And of course, you know that we have minus here and we already have minus here. So it's supposed to be something like this, 0.77 minus, already there is a minus here, and then we have this minus sign here, so it's going to be minus 0.34. So minus times minus is plus, so we have 0.77 plus 0.34. So after we add this and this, then of course we are going to get a value of plus 1.1, I think. Let me see. Let me add it and see. So we have 0.77 plus 0.34. Zero 0.77 plus plus 0.34. Yes, that will give us 1.11 volts. So this is the answer for this. And then, so the next thing that we are going to look at is another example. So let's see here, we are given another example. So we have silver 1 ion plus electron to give neutral silver. And we have zinc 2 plus 2 electrons to have neutral zinc. So we have this. So now let's understand which one undergo oxidation and which one will undergo reduction. So you see this on the value here, the lower the value, the lower the reducing property. So this one will undergo oxidation because it has low value, and this one will undergo reduction. It will undergo reduction. So after you do this, then you know that this one will undergo oxidation and this one will undergo reduction. But of course, you can see clearly here from zinc 2 plus to zinc. So we have to interchange this. We have to reverse it because this is also because zinc 2 plus here is decreasing oxidation number, so it gains an electron. So we have to reverse it, which will give us zinc 2 plus, then plus 2 electrons. So we have this. So of course here we have 2 electrons and here we have 1 electron. So we have to take these 2 and multiply this through, and the coefficient of this one, which is 1, we also multiply this. And that is why at the end we are going to have, of course, here will be 2, here will be 2, and here will be 2. So these 2 electrons will cancel the 2 electrons here. We now have, of course, zinc 2 plus. We now add it. Sorry, we have zinc. We take this zinc. We have it here. Then we now take this 2 silver ion. We have it here. And then we have, of course, zinc 2 plus here, which is this one. And then we have 2 silver ion. So we have this as the overall order of the overall reaction. So this is what happened here. And then so after this, we are now going to look at the cell notation for galvanic cell. So the cell notation for galvanic cell is usually given with some notation. So it's described the electrochemical cells. So we need to understand that there is an anode compartment which is listed at the left. So anode, we have our anode here, and then we have the double line like this, which is a salt bridge. This double line is a salt bridge. So anode is located at the left, and then cathode is located at the right. So we have this. So this is it, and then they are separated by double vertical lines. So this is a double vertical lines, which is called salt bridge. And then the concentration of aqueous solution should be specified in an equation when none. When not. So that is why here we have magnesium. So magnesium here is the first, like for example, we have, this is the anode. So the first here before the first element here before the single vertical line is the reactant, and then after the vertical line is the product. So that is why here we have magnesium and then magnesium 2 plus. So this is the product, and this is the reactant, and this is the product. And we have aluminum 3 plus here. So it's the reactant, and then aluminum metal, which is the product. So this is how to actually write a cell notation. So sometimes you'll just only be given the cell notation. And of course, once we give the cell notations, then what you are going to do is you can just use the cell notation to drive your oxidation half reaction and then reduction half reaction. That is the anodes and the cathodes like we have here. So then the next thing after this is we are going to look at, so it's actually a description of a galvanic cell that we should not forget about it. First, the cell potential is always positive for galvanic cells, so it's going to be always positive, and the cell potential is equal to epsilon naught of cathode half cell minus the epsilon naught of anode half cell. And anode is the negative terminal while cathode is the positive terminal. So we should understand that anode is negative and then cathode is positive. And then we have electron flows. Electron flows from the anode to cathode. So electrons are flowing from anode to cathode. So in galvanic cell, anode is negative and cathode is positive. And of course, there is a current flows, but in terms of the current flows, it flows from cathode to anode. So we have a positive ions that flow from anode to cathode half cell and the negative ions that flow from cathode to the anode through a salt bridge. And then we have the designation of anode and cathode. So write a balanced net ionic reaction for the spontaneous reaction. First, we have the oxidizing agent. That is the one with a more positive value. So if we have a cell potential and the one with a more positive value or less negative value is your oxidizing agent. That is your anode. That is the cathode, and then the one with the and the other would be the anode. So if you have the cell potentials for two species, so the one that have the more positive value will be considered as the anode, while the one with a lower negative value will be considered as a cathode. So I actually gave this example when you have a cell potential of 2.1 and then 1.1. So the one with 1.1 will be the anode, and then the one with 0.1 will be at the cathode. And of course, oxidation takes place in the anode half cell, and then reduction takes place in the cathode half cell. And anode is negative while cathode is positive. And there is a formula that shows the relationship between cell potential, free energy, and electrical work. And the formula is here, delta G, that is the standard gives free energy. The standard gives free energy here minus NF epsilon naught. N here stands for the number of moles, while F is a Faraday's constant, while epsilon naught is a cell potential, and delta G is the standard gives free energy. So this formula is important, and we are also going to solve some problems or some questions related to that in our next video. So then the next thing after this is of course Nernst equation. It's a Nernst equation. So a Nernst equation is an equation like this. We have a cell potential, and then it's equal to standard cell potential minus 0.0591 divided by n log Q. Q stands for the action quotient, or in some other case, it can be the chemical equilibrium. And you know that, so the equilibrium constant. So to express the reaction using in terms of the equilibrium constant, we usually take the concentration of the product divided by the concentration of the reactor. So ladies and gentlemen, if this is the first time you are coming to my YouTube channel, please subscribe. And in the next video, we are going to look at questions that are associated with this three formula from this video, and then we'll actually solve the questions. Thank you. Please subscribe.